Why are acids and bases important for understanding how organisms work? So here's an image of the different pH values in different organs in the human body. Okay? So some pHs are going to be very low, and we're going to learn that very low pH values mean an acidic environment. Okay? And higher pH values are going to be more of a basic environment. Okay? So the point here is for you guys to see that different organs have different acidity or basicity levels. Okay, some organs are going to be basic, some acidic, and some neutral. And this is going to depend on the kind of function that they have. And this is why it's important for us to understand acid-base chemistry. So let's define acids and bases. What do we mean by that? Okay, so the earliest definition of an acid was given by Arrhenius. So let's look at the acid definition first. An acid contains a hydrogen atom and dissociates in water to form a hydrogen ion, which is H+. Okay, so let's look at HCl, which is the example acid here. Okay, normally hydrogen has its one valence electron, okay, and that is going to pair. I'm actually going to change the color. Let's do hydrogen is going to be in green. Here, let's do this. Hydrogen is going to be in red with its one valence electron. And I'm going to write chlorine in green. Okay, so chlorine has 7 valence electrons. And normally what happens here is these two will form a covalent bond, where HCl is now a covalent compound. Okay, but what's going to happen is that when we put this covalent compound in water, the hydrogen is going to dissociate. What this means is that that one valence electron that it has, it's going to leave it behind with chlorine. And then it's going to come off as an H+, because it has left its one valence electron behind. Okay, think about the hydrogen atom though. The hydrogen atom, the neutral, has one proton and one electron. So when HCl dissociates in water, this one electron that normally belongs to hydrogen has now been left with chlorine, leaving chlorine with a negative charge. Okay. But what is left is just a proton, basically, because hydrogen only has one proton and one electron. If it's one electron, it leaves it behind. Now it is just a proton. Okay. So sometimes you will see H+ be referred to as a hydrogen ion. Other times it will be referred to as a proton, because it literally is just a proton. Okay. So HCl dissociates into a proton or a hydrogen ion, H+, because it leaves its valence electron behind to chlorine, and it produces a chloride ion because it now has an extra electron. So this is what we mean by an acid. So when we're thinking about acids, we are going to be tracking this proton or this hydrogen ion. Now let's look at a base, the definition of a base according to Arrhenius. So a base contains hydroxide. And that means that when it dissociates in water, it'll form OH- ion. So let's look at this one here. This is going to be, NaOH is going to be a neutral compound. An ionic compound. It's neutral, but it's also ionic. And when we put an ionic compound in water, what it will do is it's going to dissociate into its constituent ions. It's going to dissociate into Na+ and OH-, which is a polyatomic ion that we have worked with. So for a base, if your compound has an OH in it, then this is going to act as a base by definition. All right, so Arrhenius was generally correct, but it did have some limitations because sometimes it was just a little bit inaccurate. One of the inaccuracies is that H+, or this proton or hydrogen ion, actually does not exist in water. Instead, what happens is that H+ reacts with water and it forms what we call the hydronium ion, or H3O+. I will be using the term hydronium ion in this lesson. Okay. So down here, I'm showing you the equation that we looked at in the previous slide, where we had HCl and it would dissociate into H+ and Cl- ion. Okay. But in reality, H+ does not exist. What H+ does is it reacts with H2O to form H3O+. How does this happen? Well, we have our oxygen bonded to 2 hydrogens. This is H2O, and this oxygen has 2 lone pairs here. So what will happen is H+ is going to come in without any valence electrons. And what the water molecule will do is it's going to donate these two valence electrons here. I'm going to write them in green. These two valence electrons here, these two lone pair electrons, both of those are going to be donated to form a bond with that H plus, which currently does not have any electrons. So these two will now form a bond here, okay? So now you have H3O plus, because now you have 3 hydrogens, but the reason it's a plus is because it accepted an H plus. Okay, so now it has an extra proton. All right, and that's how we get H3O plus. So in reality, how we should write our chemical equation is not like this, but we are going to write it like this, where HCl is still going to dissociate into Cl minus and the positive species, but this species is going to be a hydronium ion, H3O plus. Okay, so sometimes you will see H3O plus used, sometimes you will see H plus, but it's important to note that H plus does not actually exist. It's just a shorthand way of writing it. What actually exists is this H3O plus, but they are used interchangeably. Okay, so this leads us to the Bronsted-Lowry definition of acids and bases. So what is this definition? Well, a Bronsted-Lowry acid is a proton donor, okay, or a hydrogen ion donor, okay? So what this means is that anytime that you need to identify an acid, that compound needs to have a hydrogen that it can donate, okay? So in this example up here, the chemical reaction we've been looking at, which is HCl with water, we can see that HCl is going to donate this hydrogen, it's going to give it to water. That's what we mean by donate, okay? And it's really a hydrogen ion, what it's donating, okay? So acids are proton donors. What is a base? Well, it's going to be the one that accepts the proton. So in this example here, water is actually going to be, by definition, our base. That's because it's accepting a proton. And we know it's accepting a proton because H2O becomes H3O. So now it has an extra hydrogen and that positive charge, which is coming from the proton, okay? Because what's being transferred is an H plus. Another way to visualize this reaction is with this space filling model, okay? This is going to be your hydrogen, this white sphere. This green sphere is your chlorine. Okay, this here is your H2O. Again, these two are hydrogens. And then the red sphere is your oxygen. So what is happening is one of these hydrogens here is now bonding to this H2O to make it H3O with a positive charge. Okay, and then Cl stays behind with that valence electron from hydrogen that it left behind, and that's why it's Cl minus. So this is how we define Bronsted-Lowry acid and a Bronsted-Lowry base. An acid is a compound that has a proton that it can donate, so it's a proton donor. The base is going to be a proton acceptor, so it needs to have those lone pairs available in order to make that bond with the proton. Okay, here are some common acids. Again, what you will see is that a Bronsted-Lowry acid must contain a hydrogen atom. We will often draw a generic acid in this way, where we denote this hydrogen here, which is the important part. That's the proton that will be donated. Okay? And then this is just a generic way to write the rest of the acid. So what you'll notice here in the acid column is that all of these compounds have a hydrogen they can donate. Okay, so you have hydrobromic acid, phosphoric acid, and so on. Okay, so all of those hydrogens will be available for donating. I also want to note that they don't always have to be neutral. Acids can come with charges. It can have a positive or it can have a negative. Okay? That doesn't matter. What does matter, however, is that it has hydrogens that it can donate, okay, as a proton. I also want to note acetic acid here, okay, for 2 reasons. One, this acetic acid doesn't have its hydrogen in front, like all of these other acids have hydrogens written in front. But it does have an acidic hydrogen. That hydrogen is going to be this one here. Okay, it's the one that is bonded to the oxygen. So that's the first thing. This hydrogen can be donated as a proton. The other thing I wanted to note is that not all hydrogens in a compound can be donated. So look at these H3 here, these 3 hydrogens are these hydrogens here. The hydrogens that are bonded to a carbon are never donated as a proton. So these hydrogens cannot act as an acid. However, this hydrogen can. Okay, and that's what makes acetic acid an acid, is because it has that hydrogen there. And this hydrogen is part of the carboxylic acid functional group, which is a functional group that we will talk at length in the next unit when we talk about organic chemistry. Okay, so that is the definition of an acid. What about a base? Well, a base is going to have this electron pair that forms a new bond to the proton from H2O. Okay, so let's look at this reaction here. What is happening? Well, we see that NH3 here has accepted a proton because it now has 4 hydrogens and a positive charge. Okay. And what we're going to see as well is that that proton came from water because H2O has now become OH with a minus. So what this means is that H2O transferred a proton to NH3. So what this means is that NH3 accepted a proton, and that is the definition of a Bronsted-Lowry base, is accepting a proton. Okay. Now again, in order for it to accept a proton, it must have that lone pair, which nitrogen does. Okay. So here are some common examples of Bronsted-Lowry bases. Again, here are those lone pairs that are important for bonding to that proton that is being transferred. Okay, but you can also have the OH base coming from your ionic compounds, because OH also has, this is the Lewis dot structure of an OH atom or molecule. Okay, it has a minus charge. What you'll notice is that this oxygen still has lone pairs there that it can use to bond to a proton. Okay, so that is why OHs from ionic compounds are still considered bases. Okay, let's apply what we've learned so far. Which of the following species can be Bronsted-Lowry acids? Okay, so in order to have a Bronsted-Lowry acid, there's one requirement. It must have a hydrogen that it can donate. So HF, it has a hydrogen and it can donate that hydrogen, okay, because it's not bonded to carbon. All right, HSO3, it has a hydrogen here in the front. Typically, you're going to see acids with the hydrogen written in the front like that. It has its hydrogen. That will also be an acid. Cl2 doesn't have any hydrogens, so it doesn't have a proton it can donate. That is not going to be an acid. All right, now they're asking to identify Bronsted-Lowry bases. Well, a base just either needs to have an OH group, typically seen with ionic compounds, or it needs to have an ion that has plenty of lone pairs on it, maybe something like what we've seen so far, which is nitrogen, which has its lone pairs there and maybe 3 bonds. Okay, but it has those lone pairs. All right, so to identify a base, I need to have an OH. I have an OH here, so this will act as a base. Cl minus, it's going to act like a base because it's going to have lone pairs that it can donate to a proton. Okay, so this is typically my Cl minus. All right, and it can basically donate any of those valence, but let's say it'll donate this lone pair to make a bond with H plus. So, for example, this can go to, okay, because H plus does not have any valence electrons. So it's going to make that bond there. And basically what we have is HCl. Okay, so Cl minus is a Bronsted-Lowry base. What about CH4? Well, it has hydrogens, but we're looking at bases. Okay, so that means that it either needs to have an OH or lone pairs that it can donate. So let's see what CH4 looks like. The Lewis dot structure looks like this. There are no lone pairs here on carbon that can bond with a proton, with H plus, that can accept a proton. So for this reason, CH4 is not a base. All right, so now we're going to continue doing the same thing, classifying compounds as either an acid or a base, but this time we're going to do it within the context of a chemical equation, okay? So on the left-hand side, we have our reactants. So these here are our reactants. On the right-hand side, it's our products. So what they're asking here is to classify each reactant as a Bronsted-Lowry acid or base. Okay, so the first one we're going to look at is HF. In order for it to be an acid, it needs to have a hydrogen. Okay, it has a hydrogen, that it can donate as a proton. So this is going to be an acid. Okay. And what we see is that in our reaction, this here donates, it gives, or it loses, I can say it loses a proton. Okay. H2O here, H2O is gaining a proton. How do I know it has gained a proton? Well, it went from having 2 hydrogens to having 3 hydrogens, and it went from having a neutral charge to having a positive charge. So that means it gained an H plus. Okay. So if it gained a proton, by definition, that is a base. Okay. And here's a little diagram to show that. All right, what about our next one? All right, I'm trying to classify the reactants as an acid or a base. I first look at SO4 2-. I notice it doesn't have any hydrogens, so it's probably not going to be an acid. Okay. Let's see what it actually does. SO4 2- goes to HSO4-, meaning it picked up a hydrogen. So if it has accepted a hydrogen, that means this is a base. It was capable of accepting that proton. That means my H2O is probably the acid, but let's check it. Okay, what is an acid? An acid is a proton donor. So if we follow H2O, we see that H2O was converted to OH-, which means it lost an H+. Okay, it used to have 2 hydrogens, now it only has 1 hydrogen. And on top of that, it has a negative charge, which means it lost a positive charge. Okay. And that is how you classify acids and bases. Okay, so you've probably noticed so far that when a species gains a proton, which is an H+, this is the same thing as a proton, it gains a +1 charge because it has a positive. Okay, so if we have water and it accepts a proton, well, if it's accepting a proton, it's acting as a base. Okay, and because it's accepting a proton, it's going to have 1 more hydrogen and then that positive charge. Let's look at HBr. If HBr loses a proton, if it's losing, that means it's an acid. It has donated its proton. Okay? And when it does that, it's going to leave behind a -1 charge. Okay. Now, this is the same reaction we saw in the previous slides, where HF is reacting with water, and we classified it as an acid because it has this hydrogen, and the water was the base because we saw that it accepted a hydrogen. Okay. But now what I want you to notice is that on the left-hand side, we have a net charge of 0. So HF has a neutral charge, H2O is also neutral. So the entire left-hand side has a charge of 0. 0. On my right-hand side, I have F-, which is a -1 charge, and then I have a plus, which is a +1 charge. These two, -1 + 1, is equal to 0. And this is what we mean by the net charge on a chemical equation must be the same on both sides. Okay, if it's 0 on the left-hand side, it must be 0 on the right-hand side. Let's look at a slightly different example. Where here, now I have a 2- and H2O, which is neutral. So I have -2 on my reactant side. And if I look on my product side, I have a HSO4- and OH-. That means I have a -1 plus another -1, which is just -2. Okay, so these net charges are in fact the same on both sides of the equation. So when you're thinking about acids and bases or writing acid-base reactions, you have to make sure that your net charges are the same on both sides. Okay, so now we're going to put everything we've learned together in order to predict the products of a reaction. Okay, so the first thing that I notice is that I have HClO3. This hydrogen here in the front is telling me that this is likely an acid. Okay, so what this means is that ClO3 is going to, or HClO3 is going to dissociate. Specifically, it's going to donate that H as a proton. So that means that this H is going to leave behind its electron. So when HClO3 loses that proton, it becomes ClO3- because that hydrogen left behind its valence. Okay. Now this is going to be aqueous because we have put this in water. All right. Now where did my proton go? Well, it's going to go over to here. It is giving it an H+. Okay. So HClO3 is going to donate its proton, and H2O is going to accept it. So that means that H2O becomes H3O because it has accepted that hydrogen. So now it has 3 hydrogens, but it also accepted a positive charge. So it's going to go from being neutral as H2O to now having a positive charge. This is also going to be aqueous. Okay. All right, so this is basically my acid base reaction. This was my acid, and H2O here was my base. Again, HClO3 is the acid because it was able to donate a proton. H2O is my base because it accepted that proton. Let's do another example. Okay. Here, I can actually donate and accept, HSO4 can donate and accept a proton. So here we're going to do an example where it accepts a proton from H2O. So H2O is actually going to donate that proton. Okay. So what's going to happen is that H2O, because it has donated that proton, is going to become OH minus. Okay, so it lost a hydrogen, but on top of that, it also lost a positive charge, which is why now it has an overall negative charge. This is going to be aqueous. And now HSO4 minus has accepted a proton. So now it's going to have 1 more hydrogen. So I need to write that as H2. SO4. And this minus charge goes away because a minus and a positive equals 0. So that's why H2SO4 is now neutral. And this is also going to be aqueous, okay? Because it's all in water, all right? So this is how H2O can act as an acid and HSO4 minus as a base. Again, H2O was an acid here because it donated its proton to HSO4 minus. Oops. Okay. So from here, this is what how we can predict the products by understanding the definition of an acid, which is a proton donor, the definition of a base, which is a proton acceptor. Okay. So now we have terms that we use to define the products that an acid makes or that a base makes. So let's look at this generic acid here, just HA. A can be anything or many things. This hydrogen here is the one that we're keeping track of in terms of where it's being donated because it's an acid. Okay. So when an acid donates its hydrogen, it becomes an A minus, right? Because it donated that proton basically, right? We call that the conjugate base. So HA, whatever this acid leaves behind, which is now my product, we call that a conjugate base. If we look at the other reactant, which was originally a base, if it accepts that proton, it's gaining the proton, it has now become a conjugate acid. Okay. So identifying conjugate acid-base pairs will be relevant for understanding how buffers are going to work. And it's also just relevant in when we talk about species in an acid-base chemical reaction. So let's look at an example of how to label these, okay? So this is the same reaction we just predicted the products for in a couple of slides ago, okay? We predicted ClO3 minus and H3O plus, okay? So let's go to our reactants first. HClO3 is going to be an acid because it has this proton that it can donate, okay? Acids are proton donors. Bases are proton acceptors. We said H2O was a base because it accepted a proton. So let's look, HClO3 becomes this ClO3 minus, okay? So that means that this is going to be its conjugate. I'm just going to write CONJ for conjugate. Its conjugate base, okay? So an acid makes a conjugate base. So we say ClO3 minus is the conjugate base of HClO3. Right. The other thing you'll notice is that the water, the base here, is now going to become the conjugate acid. So the conjugate acid of H2O is H3O plus. Let's do the same thing for the other reaction that we predicted. Okay. So H2O becomes OH minus. What this means is that H2O donated a proton. So this was an acid. That means that this is going to be its conjugate base. Okay, HSO4, this was the base because it accepted a proton. Okay, I'll write that down here. So that means, whoops. So that means that this is going to be the conjugate acid. Okay. So HSO4 minus as a base, its conjugate acid is going to be H2SO4. Now, I want you to notice something on this slide. We have H2O in the equation above, in the chemical reaction above. It's acting as a base, okay, where it's accepting a proton. In the second reaction, H2O is acting as an acid. It is donating a proton. Okay? So this characteristic is what we call amphoteric. Okay, so water is an amphoteric compound. What this means is that it's a compound that can act as either a base or an acid. And it can do this because water has a hydrogen it can donate. That's what makes it an acid. But it also has lone pairs that it can use to accept a proton. So if we look at water up here as a base, it's a base because we're adding H plus to it. It's accepting an H plus. So you can see that when water acts as a base, its conjugate acid is going to be H3O plus. When acid is behaving, when water is behaving as an acid, meaning it's donating an H plus. When water is an acid, its conjugate base is OH minus. Okay, and this is how we talk about these species. All right. So like H2O, HCO3 minus is also amphoteric. Means it can behave both as an acid or as a base. So in A, they're asking me to draw the conjugate acid of HCO3. Okay, so let's start with HCO3 minus. They're asking me to write the conjugate acid. So if I'm writing the conjugate acid, that's what they want. They want conjugate acid. That means this is going to act like a base. Okay, so base with its conjugate acid. That's what we mean by a conjugate acid base pair. All right, so if HCO3 is acting as a base, that means it must be accepting a proton. So we're going to add H plus to it. So what this means is that the conjugate acid is going to be H2, because I've added a hydrogen, CO3, and then my negative charge goes away because a negative and a positive equals 0. Okay. Let's do the same thing here, but now for a conjugate base. So I want a conjugate base. That means that I'm starting with an acid. So if HCO3 minus acts as an acid, that means it's going to donate or lose an H plus. It's donating it. So if it loses its H plus, that means I no longer have that hydrogen. So I'm left with CO3. And now I had one negative charge. Now I have lost a proton, right? So I'm going to gain another negative charge here. So now I have a 2 minus because I lost a positive.